Welcome, everybody, to The Blind Spot. This is a podcast about science and philosophy and other things. The location, the cultural intersection between science, philosophy, and human culture. And what we try and do each time is take on a subject that's near and dear to our hearts. I'm with Marcelo Gleiser and Evan Thompson. We are the authors of the book, The Blind Spot. And each time what we want on to do is pick up on some topic. Maybe it was covered in the book, or maybe it's adjacent to the book. And today what we're going to be talking about is time, right? One of the most perplexing, most fundamental issues in both physics and philosophy. So, let's get right into it. So why don't we begin with the Greek ideas about time, because so much when it comes to science rests on Greek philosophy. So Marcelo, why don't you get started and just sort of tell us a little bit about, how those ideas from the Greeks ended up in science.
Yeah, thanks, Adam. So this is a topic that I absolutely love. So just interrupt me if I get too excited and talk too much, please. Okay. Because I think the Pre-Socratics were just awesome, right? I mean, some of the most spectacular and fundamental ideas that are still with us. These guys, we're talking 650 BCE, right? So almost 2,700 years ago, they were asking questions about nature. And contrary to their predecessors, this group of thinkers from Miletus in particular, which is now the western coast of Turkey. That's where it started. Instead of invoking gods to explain natural phenomena, they actually tried to find answers within nature, right? So that is a fundamental shift in the way people in general dealt with the nature of reality, right? So instead of saying the gods, for example, if you had asked a Greek at the time, how does the sun go around the earth? Because, they were thinking always from an earth-centered or geocentric perspective. They'd say, well, the god Helios with the fiery carriage would take the sun from east to west every day. And those pre-Socratic philosophers said, there must be other ways of thinking about this. And so instead of invoking gods, they were invoking ideas about nature. And just because the topic today is time, very broadly, you can classify the many different kinds of schools in pre-Socratic philosophy into two fundamental classes. One is the philosophy of becoming, the idea that nature is always in a flow. It's always a transformation. And for example, the first, according to Aristotle, who wrote about 300 years after these guys, and actually criticizing them, but we don't have a lot of stuff from them that survived. He would say that the first philosopher, which really means the first Western philosopher that we know of, was Thales of Miletus, right? And he would say that everything was water. And why water? He said, that's stupid. A rock is not water. Well, so you can't think of this in a very concrete way. You have to think of it in a metaphorical way. That what he meant by everything is water is that water flows, water transforms, from liquid to solid to vapor. And so to him, it kind of represented the eternal changes that you see in nature, right? So that's the Ionic school, the school of becoming. Another great guy that comes at the end of this school is Heraclitus, who is really famous, right? Because everybody quotes him and saying, yeah, he's the guy who said that you can never step on the same river twice. He didn't quite say that, but it's close enough. And you say, why not? And his answer would be, well, because the second time you come by, the river is not going to be the same river, and you are not going to be the same person, because everything is always changing, right? So, nutshell, that's the school of the thinkers of becoming, transformation, nature in a state of flow. And then you had also in the southern coast of Italy, you had Parmenides. So Parmenides was exactly the opposite, right? So this is great because one goes, oh, everything is a flow. And Parmenides says, no, sorry, folks, no flow. What's really essential is that which cannot change, which is eternal. And he talks about the eon as the unchangeable, the fundamental nature of things cannot be a changeable things because then it's not fundamental, it's flaky, right? So if something changes, it becomes something new, and then it cannot be fundamental. So to him, what was essential was the unchangeable. And that is the philosophy of being. If you want to know the truth, you go for the things that are eternal, the things that do not change.
Eternal, right. Yeah. It's interesting just how often in human conception, when, in philosophy or just in human, the attempts to understand the world, it's always dualities, right? This idea of, the binaries, right? And I forgot who the anthropologist was. Was it Levi Strauss, who talked about the cooked and the raw? That almost always human beings always end up having, not 3 or 5 or 12. It's always, we tend to parse things into duality. So being and becoming were, as you're saying, is already the beginning of the conception of time for the lineage, the philosophical lineage that would lead to Western science.
There's another dichotomy that we can pull out of the Pre-Socratics, since we're talking about the Pre-Socratics. I also love the Pre-Socratics. And this is a dichotomy that the philosopher R.G. Collingwood calls attention to in his book, The Idea of Nature, which is a fantastic, one of my favorite philosophy books, actually, The Idea of Nature. We cite it in The Blind Spot. So he says there are the Pre-Socratics who were really concerned with substance, like Thales, who says everything is water. And then there are the Pre-Socratics like Pythagoras, who are really concerned with pattern, with musical intervals and with geometry. And you see these two tendencies, ramify through the rest of Western philosophy and into science. The questions of the primacy of substance or materiality or stuff versus understanding, using mathematics, using pattern and mathematical intelligibility. And that's a big theme in our book, The Blind Spot, of course, where the incredible insight that patterns can be, fundamental, the musical interval, the geometrical ratio, and then in the way that we talk about it, then the way that can get reified so that the pattern takes on a life of its own, independent of the concrete phenomena that you originally encounter it in. And that's what we call in The Blind Spot the reification of mathematical entities. So that's another element in the mix, substance, pattern, being, becoming, time. They're all interwoven in these thinkers.
Yeah, I think one thing for people to understand is that, for the three of us, we all deeply love science. We all do science and philosophy. But what sort of our view sort of sets us apart often, then we get into trouble with our colleagues, maybe or maybe not, is our sense that, this idea of the eternalness, like of mathematics, that math, and you see this in the beginning with what, as Marcelo's talking about, with the people who are focusing on being, the idea that mathematics somehow is eternal and independent and, exists in a kind of, the mind of God, was something that you can see, right, being set early on here with the Greeks, especially with respect to time.
Yeah, and Plato, if you think about what happened there, and I think, Evan, please correct me if I say silly things, but, Plato brought in a weird combination of all these things, right? Because he had the Pythagorean mathematics in his philosophy. He also thought that mathematics was the way to the truth, so to speak. People talk about the Platonic solids, right? That the 5 Platonic solids, that we know of, so we have like the pyramid, so it's 4 triangles, and then you have the cube, which is 6 squares, and then you have the octahedron, the dodecahedron, the icosahedron. So there are only 5 closed solids that you can build with simple triangles, squares, and pentagons. And that is a model of geometry, which is really beautiful, because then what Plato is going to do is going to use these 5 solids to represent everything that exists. So he uses each one of them will be used for the 4 elements. So you have earth, water, air, and fire. He's going to use each one of these solids as an atom of these things. And then for the cosmos, he used, because he needed a 5th, so even though there are 4 elements with Empedocles, I said, I need a 5th, damn, what do I do? Oh yeah, that thing is almost like a sphere, and he used the 5th one to represent the cosmos, right? So his construction of nature was based on patterns. That's why it's cool what Evan was saying, and if you think about it, this is so much the lifeblood of physics nowadays, right? Because in physics, we talk about transformations. The mathematics of physics is calculus, which is about mathematics of change. Derivatives is about changing. Velocity is how you change your position in time and you take a derivative. So that's changing. But we always talk about the laws of nature as being immutable. They don't change. So you have the being and the becoming, in a sense. The physics is about, look, the world out there is changing and we're going to map this change through our equations and etc. But then, right, we are looking for those laws which are supposed to be unchangeable, supposed to be the being, the fundamental structure of reality.
Yeah, which is something. So, Evan, could you sort of talk about that as we're sort of making because the next thing I think we want to talk about is how, in the medieval period, the scholastics, who were all, deeply embedded in a Christian sort of worldview, how that the idea of reason, and this idea of immutable reason, of reading God's mind in the laws of nature, how did that emerge? How was that carried forward, especially because a lot of Western science was built out of, a culture that was deeply Christian, or deeply Catholic, or deeply religious with a monotheistic God. Could you take us through kind of the transition as we're heading towards the Renaissance and the birth of science? What happened?
Yeah, I mean that's a lot of time and space to
I know.
cover.
Snap it up, buddy.
Yeah. And it's not my area of expertise in philosophy, but one thing I would say is that so it's not just Christianity, of course. Islam plays a huge role, in the history of science, the history of mathematics, and the Jewish tradition as well. But I think, if I were going to pull out one sort of overarching idea, it would really be this. We talked a little bit about this in our opening episode. It would be this idea of a universal intelligibility to the cosmos, that the cosmos has an intelligible structure and mathematics is the way of rendering that. And this is very different from the modern worldview. We are actually embedded in it and participants in it, so that the microcosm within us and the macrocosm without us have this intelligible unity that we render in a mathematical language. And that's very different from a modern view where you get nature re-described as a mechanism that's looked at from the outside by like a deist god. So this is, of course, much later, say in the 18th, 19th centuries, we get this idea of the universe as kind of a clockwork machine, and God is external to it, and God creates it, and then it sort of just runs on its own. That's very, very different from the ancient worldview, with the understanding of what's constant or universal or invariant and what's undergoing change, all of which has this, beautiful, formal, geometrical structure of intelligibility to it that, Plato, of course, plays a formative role in describing the intellectual architecture for that vision.
Yeah, I think that's a really important point, because I don't think people sort of understand how we got to a world now that seems dead, right? Science seems to describe this dead world, and it's just atoms bouncing, an insentiate universe that, with just atoms bouncing randomly into each other, obeying the laws of atoms bouncing into each other. And actually, up until like Newton and even Laplace, I was just reading this, but certainly Newton, the idea that the universe had that there was a God there who was, sort of had rationally planned the world, was part of reason, or was reason itself, and human beings were participating in this. That losing that is pretty recent. I think it's important for people to understand that was even in science itself, that was the late 1700s and 1800s. When science was born with Descartes and Newton, these guys were still pretty deeply religious and had a view of that kind of God.
So can we go back to the Pre-Socratics for a second? After Thales, his student was called Anaximander, and Anaximander was the first cosmologist. That's why I wanted to bring this back, because this is really mind-boggling, right? Because people at the time would look at the sky and they would say, yeah, you have stars that blink and don't really move very much. They're always in the same place. They move, of course, as the whole sphere, the cosmic sphere kind of is changing. But then we have the planets, right? Which, by the way, the word planete, which it means wanderer in Greek, because they already knew, and the Babylonians way before them also knew, these things are moving in the sky, right? And Anaximander had this incredible insight where he said, I know that the sun is moving around the earth from east to west and everything else is moving in the same way. So what if, he says, and this is the first mechanical model of the cosmos. That's why I wanted to bring this up, because I think it's so interesting. He says, if the earth is the center, imagine that you have like bicycle wheels. They were not bicycles. They were like those, what do they call again? Those chariots, right? The wheels of chariots with the spokes, etc. But then they had the wheel, and inside the wheel, instead of the bicycle that has air, it had fire. And what he said is that it turns out that the earth is surrounded by these wheels, and the sun happens to be a hole in this wheel. And so the fire escapes and the wheel is turning around, and it turns around the same way every day. And that is why we see the sun. So the sun is the fire coming out of a rotating wheel. And so then he says, and so is the moon, and so are the stars. And so basically he created this geocentric model of wheels turning around, carrying this fire. No gods, just mechanics, right? And this is 640 BCE, roughly. And then what is going to happen, with Plato, but certainly with before him, there are other guys, like Aristotle came up with a model of spheres within spheres, 56 spheres within spheres, to explain every motion of the cosmos that they could see, still Earth-centric, of course. And that is totally mechanical. But there were issues, there were issues because, for example, they knew that, and this is interesting because it shows you how the scientific imagination kind of resolves problems, right? So, for example, we see that the brightness of planets and of the moon changes because we know that the orbits they are elliptical, and so they come closer to us and move far away. And so Mars is brighter now than yours, blah, blah, blah. But if you are stuck in a wheel, or in a sphere, that doesn't happen, right? So how do you solve that? So 150 CE, so already Ptolemy, right? Claudius Ptolemy came up with his model of the epicycles, where you had this Earth in the center, not quite in the center, but again, you had wheels, but then you had little wheels attached to the big wheels, right? And with that, you could change the location of the planet, and then you can have brighter or not so bright. And this model of Ptolemy, I need to say this because it's so amazing, was accurate like a machine, predicting the position of all the planets, visible planets, to within a full moon. So it's about half a degree in the sky, which is basically you stretch your arm out and you look at your thumb. That's about a half a degree of the sky. The guy, so you could say, where is Mars going to be in August 27, 2030? Oh, no problem. You just crank the wheel and you get it. And why is this interesting? Well, first, because of the focus on precision.
Yeah, which is an important part eventually of why science becomes so important, why culture adopts science.
Yeah. And the other one is the notion that he wanted to do this by using these concentric spheres, spheres within spheres, etc., because they thought that the best possible way a universe could be designed by a clever God. God comes back after the Pre-Socratics, right? And that's kind of not the Christian God, but was using the most perfect object that we have, which is a sphere or a circle. So everything was about finding models of the universe that were predictive with using spheres and circles.
And spheres, and there was thing about about becoming versus being. While there was change, right? Things changed, but it was like perfect and unchanging. The sky itself, the machinery, was eternal and unchanging. The rules were eternal and unchanging, as opposed to change on Earth, where like things died and decayed and smelled bad. And that's important because now, let's accelerate time-wise up to about 1200, 1300. And there's a group of scholars in Europe who are trying to understand change in a way that was really quite radical, right? So according to Aristotle, there was a bunch of different kinds of changes. Most of them were really hard to get a grasp on, but movement through space, right? Seeing the cart's over here, now, and in a half an hour, the cart will be over there as it moves along slowly. That kind of change, these scholars who were called the scholastics,
the Merton College,
right.
College in Oxford.
They were the first ones to get start developing the idea that, that kind of change, which was really only one of a handful of the kinds of change that Aristotle talked about, that one is mathematizable. That one you can actually represent on a graph with like one axis being time and the other axis being position. And then whatever line you get, whatever trajectory on that graph is, you can do mathematics of that trajectory. And we should just spend a moment talking about why this was so important, because it was the beginning of saying beyond just the heavens, even here on Earth, you could describe one kind of change, which was motion, or kinematics as we called it, in terms of various kinds of mathematical equations. And that's going to have a huge influence on the science, how we view science today. So maybe we can just, start, Evan, I don't know if you want to maybe start with that. Just why was that so important from a philosophical point of view for what's going to come later?
Yeah. I haven't really studied the Mertonians that much. And I remember when we were writing our book that you were writing those sections, and I had to go back and remind myself. I had studied some of that as an undergrad in history of science, and it's kind of a fascinating transitional period, right, where you have a different understanding of change and its relationship to motion starting to emerge, and we have a tendency to read it retrospectively in light of the successes that came afterwards. And I can't do this because I'm not a specialist of this, placing yourself back in what they were thinking, not viewed from where we are now, or even where things wound up in the 17th century or 18th century. That's a historians do that, right? They put themselves back in the period and really reconstruct it. And I'm not actually able to do that because I don't know the materials well enough. But it does seem to be a kind of pivotal transitional moment to what emerges later that we see with the understanding of motion and inertia and things that really Galileo we think of as the pivotal person for in early modern science. Yeah.
Yeah, that's the I think the big transition there with the Mertonians at Oxford, I think was mid 1300s, something like that, perhaps even a little earlier. And William of Ockham,
even a little bit earlier than that, right?
And people like that, and what's his name, the Bacon guy, not Francis Bacon, the other, Roger Bacon.
Roger Bacon.
And to me, what's really amazing is that they figured out that you could represent something that was happening in the world on a piece of paper, change as something that could be a graph, right? That you could put the position as a function of time, and then you could calculate the area, and that is to me kind of remarkable that they are beginning.
I think because it just struck me as we're talking about. Really, what the Mertonians did that no one had ever thought of before, as you're saying, is they represented time as space, right? There was an axis you could draw on a piece of paper, and you could mark out 1 second, 2 seconds, 3 seconds, 4 seconds, and it was time is. And I recall when I was doing the research for that chapter, what was happening was they were doing something else. Actually, it started. They were trying to represent an iron bar. The temperature, the hotness of an iron, they didn't have temperature yet, but the idea of the hotness of an iron bar where one part was in the fire. And so they had drawn a graph of the bar space, 1 inch along the bar, 2 inches along the bar, and how hot it felt. That would be the other axis. You could have a plot of how hot it felt versus the distance along the bar. And then the idea of substituting time for the distance along the bar, the spatialization of time, is something we're going to get to as we dig deeper into this. But I think that's really the important thing now that as we're talking about it, it was the first spatialization of time, which goes to this idea of like, if time is flow and you can never grab it, you can never grab this moment. It's this abstraction that you did of saying like, no, I can represent all of time as a line and identify myself somewhere on it. And that we're going to see is actually going to both be a revolution. There's a lot of genius in it, but it's also we think is going to get us into trouble later on.
The only thing I would say, just to qualify that a little bit, is I think that the idea of spatializing time is really deep. So, a sundial is already a spatialized representation of time.
Yeah.
The Mertonians have a kind of breakthrough in the mathematics that is really, pivotal for the emergence of mechanics, I guess. But that idea of time as something that you can capture almost in a spatial device, a spatial tool, and a spatial conceptual system, that probably goes back deep into the upper Paleolithic or something. It's so basic to the human cognitive architecture, and you see it in clocks. The oldest like water clocks, sundials, that's already present there.
Yeah. So I think it's the mathematization probably that maybe that is unique. All right, so let's go on to Galileo. Let's finally get to Galileo now. We're half an hour into this. This may be a 2-part episode. But all right, so Galileo, and let's talk a little bit about how, in order to develop modern physics, modern mechanics, you need time. So let's just talk about Galileo and Newton in order to set the stage for then going forward to Einstein. So Marcelo, do you want to talk a little bit about like what Galileo did and Newton as well? Let's cover both Galileo and Newton and their views of time, and how that established, the foundations for modern physics.
Yeah. So perhaps the best way to contextualize that is, when I teach my course Physics of Poets at Dartmouth, one of the things that we do is we repeat very important experiments that happen in the history of science, right? And perhaps Galileo's most important experiment was his inclined plane, right? That he puts a ball on top of an inclined plane and then lets it roll and then measures how long it takes for it to go down. And then he changes the inclination of the plane and does it again and stuff. And he was doing that because he wanted to study free fall, how objects fall down, right? But a ball falls down too fast, if you're just like 1 meter high, like from your height or something. So by doing this inclined plane, he slowed down the motion so that it could be measured. But there were no clocks that could measure, time at their accuracy. So what the heck did he do to measure the time? So this is amazing. So one of the things that he did is he used his pulse, right? So how many heartbeats does it take for the ball to roll down? But then, of course, you get too excited, your heart accelerates. And then, oh my God, I got a result. And then you can't do that. So, you can, but it's not very accurate. Then his father was a very famous musician. And so he grew up, within this music. And it turns out that the human brain is incredibly good at keeping rhythm, like especially if you have like military marches, like ba 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 ba. I shouldn't even be singing that song right now, but think of and you can really do that very clearly, and that helps because you can see how many intervals of time, tum tum tum, you have as you're doing that. But the one that he ended up using in his experiment, allegedly, it was a bucket of water. So that's what I have my students do. So, one student holds the ball on top of the inclined plane. The other one has an inverted vat with a lot of water and a spigot that you open when the ball is released, right? So as the ball is rolling down, the water falls, fills up a bucket, and then you weigh the bucket, and the weight is proportional to the time. So the longer it takes, the more water. And you can use that to say, okay, I know how long it went, I know how far it went and how long it took by weighing the bucket. And he did it that way. And then we compare it to one of those spark plugs, like that goes every time the ball is moving and every fraction of a second, it makes like a little tick. And you can see how it's accelerating now because of free fall. And you compare the two, and it's kind of astounding that he actually got these results, and he got them right. So basically the result.
Right. It's astounding. That actually worked very well compared to a modern time measuring device. It actually he did quite well. That's what you're saying.
Yeah, and his jump was to say, I can convert what I just saw and measured into an equation, right? And his equation is that the distance covered by the free fall is proportional to the square of the time, right? And that's what happens on a free falling body, right? And I think that is remarkable. I wanted to mention that. And the other thing that he did was really cool is not very far from us here, in Pisa, in the cathedral, they were lighting up the candles, right? The big chandelier, lots of candles. So the guys bring it closer. And then he released it. And then the pendulum, it becomes just like a pendulum motion, right? And Galileo's like, wow, this is really amazing. How long does it take for it to complete a period, right? And again, he's using his heartbeat, and he realizes there is a very simple relationship between the period of the pendulum and not so much the oscillation, but the length of the pendulum. So he goes home and is like, how am I going to make an experiment? And this is really, I think, fundamental for what we want to talk about a lot in the show is I don't need to go back to the church and light up a chandelier full of candles. I can just get a stone, tie a rope to it, and then let go of the stone, and the stone is going to oscillate. And the same rules that are describing what happens to the motion of the stone are the rules that describe the motion of the chandelier. And that is how you bring the world into the laboratory to be able to quantify what you can see to come up with mathematical laws of nature.
Right. Okay, so now we have Galileo, who sort of like first, he's sort of building on the Mertonian sort of idea of kinematics. You're going to look at motion and change, and then finds this universality, right? Where, the swinging chandelier in the church is the same as the swinging rock in his own laboratory at home. So, time now is becoming really a fundamental sort of characterizable part of kinematics and now mechanics. So people should understand kinematics is motion, the analysis of motion. Dynamics is going to be the understanding of the forces that produce motion. And so Galileo has the idea of inertia. He's the one who recognizes that, things will keep moving unless you act on them, a force acts on them. But then it's Newton who comes along and establishes the real relationship between motion and force. And so in particular there, let's talk a little bit about the role of time there, though, in Newton's. So, Newton comes up. We don't have to go through the Newton's three law or the Newton's laws of motions in any kind of detail. But let's just talk about the role that time plays in those. And this is the first time the idea of the laws of motion, right? This is what Newton gives us, is that there are laws, as if like in legal courts, there are laws that nature has to obey. Let's just talk a little bit about Newton's time. Evan, do you want to, sort of?
You guys should do that because you're the physicist.
Okay. I'm happy to.
Yeah,
I'm happy to talk about Newton. I'm a big Newton guy. I love him. So it's not a very lovable guy, but I love what he did. He was kind of an amazing dude. Even though, I don't know about you, Adam, when you're teaching physics, I always try to tell my students that physicists are just like normal people, that we're just like everybody else. But then I said, with the exception of Copernicus, Kepler, Newton, and then they go, who were really weirdos, right? Very much so. And so Newton was very antisocial guy, right? Apparently he died a virgin. Nobody knows of any relationship with any human being more profoundly, amorous for sure that he's had. But he was a freaking genius, and he was a genius in the sense that he managed to take up on Galileo and Descartes. Let's not forget that Descartes came up in there too. And Descartes was essential because of his graphic representation of functions, right? The whole idea of the two axes and stuff that the Mertonians were doing. Descartes took that and flew with it, right? It was really beautiful what he did. we'll talk about his mind-body problem later on in another story. That's another one. But the math was awesome. And so what Newton does is he brings this together and he creates a dictionary, a conceptual dictionary to build the foundations of physics as we understand it, what we call now classical physics, right? So if you read the book, which is a horrible book to read, it's incredibly hard. First of all, it was written in Latin, but when I was 18, I tried to read it, and not in Latin, obviously, but in English. And it's all proof and demonstration. It's really like it's a book of math, but it's all about motion. The mathematical principles of natural philosophy. Yeah, the Principia, right? But he starts by defining things and says, what is absolute space? What is absolute time? What is mass? And then what is force? So he goes on with all these things. And so space, because we need to talk about space too, because, if time is quantifying change, it's changing space. So for him, space was just the stage, the background, just the thing that is out there where things happened, right? And period. So think of it as like this arena where the world exists, right? And it cannot be changed by perception or by experience or by motion or by anything else. And time is the same way, right? So he defined absolute time as the time that is always in flow and at the same rate. This is important, right? So there is no change in the flow of time. That's why it's called absolute. And it does not depend on, so if I am standing still and Adam is riding a bicycle with a clock in his hand, his tick-tock is going to be the same as my tick-tock, right? I mean, so our times are going to be the same, even though we're moving with respect to one another. So that's absolute time. No change there. And he used that to build his definitions of velocity and mostly acceleration, which was very important, and then force, right? And I think that you already mentioned, his first law is the law of inertia, that something is just going to keep going at the same constant speed unless it is interfered by the action of a force. So the force is what is going to change velocity, right? It's going to interfere with that trajectory, so to speak, right? And then acceleration is the measure of the intensity of that force. And that is how velocity changes in time.
Right. More change, always change. It's all about changes in time. With the clock, always the idea is that clock is running at the same rate everywhere in the universe at the same time. You can always define things to be instantaneous, right? You're capable of saying something is happening at the same time, no matter how far it's separated away from each other. So yeah, Newton, right? So that's just an important thing. I want to say that clock is always running at the same rate.
So we should talk a little bit about the timeline, because it's a little puzzling, right? I don't know if you guys want to say something.
Yeah, sure. I think, probably, we're already at 40 minutes. We don't want to, weigh down our listeners. So I think this episode, let's spend another maybe 10 minutes thinking about, just talking, or 10, 15 minutes about what ended, or what Newton and the beginning of classical physics left us with, in terms of, the foundations of physics, that then Einstein, we can start with Einstein next time. But, because so much, what the problem is that even with Einstein, physics and physicists still have an intuitive, so to speak, way of thinking about the world that still in some senses can be very Newtonian, of just that this, that time, the time is being something external to us, and its absoluteness.
And the timeline is the mathematical representation of this flowing time, right? So basically, you have a line, right, in a graph, and you divide it in seconds, say. So each tick is a second, and then you can, if the ball is moving, time is passing, and you say, oh, the position is here at 1 second, and let me go this way. It's here at 2 seconds. It's here at 3 seconds, and then it goes on and on. And he used that to calculate velocity and things like that. The funny thing about the mathematization of time is that if you look at it, this line is not just about a second. You could also be measuring things with the precision of half a second, or a tenth of a second, or a millionth of a second, or a billionth of a second, right? 10 to the minus 9 of a second. And so, and then you say, but wait a second, where is the moment of the present? Where is the now? If you can always find a smaller distance, time interval in this line, how do you define the now? So the now in this representation is a mathematical point in this line, right? This is a point that really has no duration.
And I think that is a good place, maybe, this idea of duration, to switch over to Evan, right? And this idea of, so Marcelo just gave us this idea that, like, right, in physics, everything, space and time are infinitely precisely prescribable, which literally also means you need an infinite amount of information to actually nail these things down, where in space you are, where in time you are. But Evan, maybe if you could talk a little bit about, this is a good place maybe to introduce Bergson, who's going to appear before Einstein, right, in some sense. And this idea of what's the problem with this idea of not having a now?
Yeah, so what Bergson does, so this is in his doctoral dissertation that gets published. We know it in English as Time and Free Will, but that's not the French title. The French title is The Immediate Givens of Consciousness. What Bergson does is his basic idea is that time is not space. So it goes back to the spatialization of time, all the way back to the sundial.
Evan, wait, can you just maybe tell, because a lot of people may not know who Bergson is.
Henri Bergson is a philosopher in France in the late 19th century into the early, and then he dies, I forget the exact year, but it's already during the German occupation of France in World War II. So he dies in the late 30s or early 40s. I forget the exact date. So he's a kind of figure of French philosophy across the end of the 19th century into the beginning of the 20th century. And his first work, which was, as I say, his doctoral dissertation, is this work called Time and Free Will. And the main point in that book is that time is not space. So he makes the point that we spatialize time when we think about it, when we conceptualize it, when we represent it mathematically. And in doing so, we lose what he calls duration. And by duration, he means flow, passage, the sense of an ever changing now, with a now that's always where you are, but that is constantly filled with, you could say, flow and change. So an example is listening to a piece of music. A piece of music is something that doesn't exist at an instant, doesn't exist over a collection of instants or a series of instants. It exists as something that has an inherent flow to it, or a dance, or the words I'm speaking now. They have a temporal flow to them, and reconstructing that in terms of instants laid out in space or laid out on a line is not really sufficient to capture the being of something that's inherently durational. And of course, nature, the world that we encounter in our perception, our experience, when we observe growth and change, say in plants or in our own lives, that's inherently durational. So you have an emergence of two different ways of thinking about time. One is the timeline with infinitesimal instance. And then you have something that has an inherent privilege now, which is where you find yourself experientially, perceptually, and the constant flow and change that animates that now. And so the big problem then, philosophical but also scientific, is how to reconcile those two different pictures of time, the one we get from mathematical physics and the one that we get from lived experience. And the one other thing I would add is that sometimes people say, oh, Bergson just means by duration psychological time. He just means time in the sense of, how you perceive it differently depending on whether you're bored or whether you're excited. Time seems to flow differently. And that's part of the experience of duration, of course. But Bergson doesn't really mean psychological time. He means actually something going back in a way to Heraclitus. He means flow and change, which is just evident everywhere in our encounter with the world. And we experience that, of course, we perceive that, we're attuned to it, but it's not something that's just happening sort of inside the head. It's something that, the plant grows from the seed into the plant and it blossoms. It doesn't go from the blossom to the seed. You start out as a baby and you become old and you die. You don't start out dead and then come into life as an old person. There's an irreversible flow, and that's not psychological. That's something that is manifestly everywhere in the world, and that our experience of duration is attuned to.
There's something funny about this, right? That there is this fundamental asymmetry between space and time that we are trained to forget when we study relativity. But before we study relativity, we're just human beings thinking about space and time, which is that we have the freedom to move in space, right? I can move left, I can move right, I can go to Europe, I can go other places. You can move in space. You have this freedom, but you cannot move in time. Time is just happening, right? I mean, if it is even, and the experiential perception of space, you look out and you can sense a distance, but you can't sense an hour in the same way that you can sense a distance. So there is something different and sort of mysterious about how we quantify the change that we experience through this thing that we call time. And to kind of like wave it away, like we tend to do as physicists, I think it's a discredit to the complication that I think Bergson was trying to kind of raise the red flag. It is not that simple. There is much more to it than just, it's just a flow that you can measure with a clock. A clock is not time.
This is kind of a good place to stop with like a cliffhanger, so to speak. So what we've done this episode, right, is we've walked through 2,000 years of human history, particularly, in the West, and its conceptions of time and the difference between being and becoming. And then we followed, the sort of the Mertonians first with a particular way of mathematizing time as a line, and then Galileo and Newton sort of formalizing that. And then this idea of this perfect mathematical representation of time is something that became inherent in physics. And it's very much the opposite of what was, someone like Bergson was trying to point out, that the human experience of time, the lived experience of time, is so fundamentally different from that. And one of the things I think we'll pick up next time, and that we want people who are listening to this to understand, is that science does not have the clear explanation for the now. It's really not there. It's really lived experience where that occurs. And so much of what we're interested in is how to bring lived experience back into the scientific domain. So next week, or next time we'll see you, we're going to pick that up, and we're going to start with the great debate between Einstein and Bergson. Wasn't even supposed to happen. It was kind of an accident. And how much the two of these giants, one of philosophy and one of science, sort of kind of battling it out, shaped sort of the received wisdom that we 100 years later get, unquestioning about, whose time really matters, and, what does the now matter or not. So we'll take on topics like the block universe, talk about time and metabolism, and then we'll even cover something called the inactive approach, which is a growing, really important new scientific way of thinking about time relative to cognition and beings and such.
Let's not forget that we will also have to talk about entropy and the second law of thermodynamics and the arrow of time. I mean, that's essential, right? Because that's all part of the debate, right? And
all right, so next time, next thrill-packed episode will start with entropy and why science tells you, or physics is trying to explain, why time flows in only one direction. Well, then we'll cover relativity, and we'll also get to the battle between Einstein and Bergson and flow from there. All right, everybody. I think that's it for today. Thank you very much for joining us, and hopefully we'll see you next time.
See ya.
Bye.
Bye.